Increasing the number of hidden layers in a neural network is a way to introduce more complexity and capacity to the model. This is often referred to as deepening the network, and models with more than one hidden layer are known as deep neural networks. Pradeep K. Suri, author and researcher. Adding more hidden layers can help a neural network learn intricate patterns and representations in the data, which may lead to better performance in certain tasks. Each hidden layer can learn hierarchical features and abstract representations of the input data. Here's an example to illustrate why increasing the number of hidden layers might be beneficial. Example, XOR problem. Consider the classic example of the XOR problem. XOR is a binary operation that outputs true only when the number of true inputs is odd. The XOR function is not linearly separable, meaning a single layer perceptron, a neural network with only one hidden layer, cannot learn it. However, by introducing additional hidden layers, the network gains the ability to learn nonlinear decision boundaries. Let's compare a single layer perceptron with a deep neural network. Single layer perceptron, no hidden layers. Plain text. Input, x1, x2, dash output, y. 0, 0 dash 0. 0, 1 dash 1. 1, 0 dash 1. 1, 1 dash 0. A single layer perceptron cannot learn the XOR function because it can only learn linear decision boundaries, and the XOR problem requires a nonlinear boundary. Deep neural network, 2 hidden layers. Plain text. Input, x1, x2, dash hidden layer 1 dash hidden layer 2 dash output, y. 0, 0 dash 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 0. 0, 1 dash 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 1. 1, 0 dash 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 1. 1, 1 dash 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 0. With 2 hidden layers, the neural network can learn the nonlinear XOR function. The first hidden layer might learn to capture simple patterns, and the second hidden layer can combine these patterns to form a nonlinear decision boundary that solves the XOR problem. In more complex real-world scenarios, deeper networks can capture increasingly intricate and abstract features, enabling the model to learn and generalize better from the data. However, it's important to note that deeper networks also come with challenges like increased computational complexity, the potential for overfitting, and the need for more data. The optimal architecture depends on the specific task and data set. Drawing parallels between the architecture of artificial neural networks and the workings of the human mind should be approached with caution, as these are fundamentally different systems. Neural networks in machine learning are inspired by the structure of the human brain, but they are highly simplified and lack many of the complexities found in biological neural networks. In the context of artificial neural networks, increasing the number of hidden layers can be loosely compared to the idea of increased complexity or hierarchy in the processing of information. However, it's crucial to recognize the vast differences between artificial neural networks and the human brain. 1. Biological complexity. The human brain is an incredibly complex organ with billions of neurons and trillions of synapses. It operates on principles that extend far beyond the simplified structures used in artificial neural networks. 2. Learning mechanisms. While artificial neural networks learn through backpropagation and gradient descent, the human brain employs a combination of synaptic plasticity, Hebbian learning, and other intricate mechanisms that are not fully understood. 3. Parallel processing. The human brain excels at parallel processing and can handle a wide range of tasks simultaneously. Artificial neural networks often lack this level of parallelism. 4. Adaptability and generalization. The human brain is highly adaptable, capable of generalizing learning across a wide range of tasks. Artificial neural networks may struggle with generalization, particularly if they lack sufficient data or encounter tasks significantly different from their training data. In the context of cognitive science, the idea of increasing the number of layers in the human brain might be associated with the hierarchical nature of information processing. Different regions of the brain are responsible for different levels of abstraction and processing. For example, sensory information is processed in lower layers, while higher cognitive functions are associated with the frontal cortex. However, this analogy is limited and shouldn't be taken too literally. The brain's complexity is far beyond what current artificial neural networks can capture, and our understanding of brain function is still evolving. In summary, while increasing the number of hidden layers in artificial neural networks can enhance their capacity to learn complex patterns, associating this directly with the human brain's complexity requires careful consideration of the vast differences between these two systems. Thank you.